invitation, Professor Didier.
Thank you very much for the invitation.
And let me introduce you here. And let me see. Okay. All right. Professor Didier is a graduate in École Normale Supérieure de Lyon, France. And he received his PhD degree in applied mathematics in 2003 from the University of Nice, Sophia, Antipolis, France, and got as an assistant professor position at the University of Toulouse, France in 2004. He completed his habilitation thesis in 2008. Since 2009, he is a professor of the University of Nice, Sophia, Antipolis, Université of Cortésie, since the 2020. Deputy head of mathematics department between 2014 and 2019. Chair of Computing and Mathematics Committee for HPC in France since 2016. His research interests are in computational methods and their applications to data assimilation, geophysics, fluid dynamics, image processing, and more generally, optimal control and inverse problem. Please, thank you again, Professor Didier Ho, and please take your talk.
Thank you. So I will give you some ideas about how to design what we call observers. The most well-known observer is nudging, which is one of the very first data assimilation scheme that was used in weather forecast. And also some backward-forward approach, specifically designed for data assimilation. So I hope the talk will not contain too much mathematics for you. Anyway, let me know if you have questions. So thanks to Alberto, you basically understood what is data assimilation. So very schematically, you have a model equation, which is time dependent, that allows you to forecast the evolution of a system. And we have sparse and noisy observations. And the goal, in some sense, is to identify the state and or model parameters of a system so that we can forecast its evolution. So there's different families of data assimilation schemes. You will hear about Fordivar, which is an optimal control method based on minimizing the distance to the observations. You will hear lots about Kalman filters and sequential methods. You will see also hybrid methods with ensemble Fordivar, Fordi ensemble var, etc. Lots of things. And I will mainly deal about something which is probably less known, which is more from mathematics and automatics communities, based on observers. Okay, so I'm considering a model which is more or less like what Alberto said, a kind of system of equations where X is my model state and F is the model itself, the function that gives the time evolution dx over dt. So I'm assuming I'm in finite dimension, in some dimension n or m or whatever. And there is an initial condition, x naught, so that if we know the initial condition, we can hopefully solve the equation numerically and then deduce the solution x at any time. Okay, so now we assume we have observations of the system, which I call y. And there is an observation operator h, which allows us to compare the observations and the model state. So as you have seen, the observations, the dimension of the number of available observations is usually much smaller than the dimension of the state itself. So that H has multiple roles. One is to basically project from the computational grid of the model resolution into the observation grid. And also you have physical change of variables, because usually you don't observe directly the model variables. So that at the end, if you know the full state X, you can apply the observation operator H of X and get a pseudo observation that you can compare with the actual observations, in the sense that they are at the same location, same time, and same physical variables. So the idea of the standard nudging is very simple. Basically, when you have available observations, you just add the red term directly in the model equation. So it's a feedback to the observations like this. So y minus h of x is usually called the innovation vector. It measures the difference between the observation and the state. And k is what we call a nudging matrix or gain matrix. So it's very similar to a Kalman matrix. So the idea is that if you solve this, even if you start from a poor initial condition x0, you can hope that after some time, thanks to the feedback to the observations, your model state x will become closer and closer to the observations and to what you want to identify. So this is well known in the automatics community as the asymptotic observer or Leuenberger observer. And as I told you, it's probably the very first data assimilation method that was used in weather forecast in the 70s. So first in meteorology, then in the 80s in oceanography. And then there has been a lot of work on how to optimize the nudging coefficients and things like that. So still it's usually used in a small break of operational centers. But here my point is to give you mathematical tools to design such a method according to your problem and to show you how it works and why it works. Okay, so first, the interesting thing is that there is a variational interpretation of nudging, in the sense that there is, you can see nudging as an optimal control method, in the sense that it will minimize some quadratic function. So if we look at the model equation with nudging here, so I am assuming quite often that things are linear. So the model is linear, the observation operator is linear. And I'm assuming that I'm using an implicit discretization of this differential equation. So the exponent n refers to time. So xn will be the solution at some time step n, xn plus 1 at some time, the next time step n plus 1. So that basically the simplest way to discretize the time derivative is simply the difference xn plus 1 minus xn divided by the time step delta t. So this is the discretized equation. And the idea is that xn plus 1, the solution at the new time step, when you numerically solve your equation with nudging, is a solution of this equation there. And the most simple way to define the gain nudging matrix K is the following in red. We basically use, so it's not mandatory, but we usually use the inverse of the covariance matrix of the observation errors, R minus 1. In order to weight more or less each observation, depending on the quality. And then the innovation vector is something that lives in the observation space. And all the other terms live in the state space. So you have to come back from the observations to the model state space. So the simplest way is to use H transpose, the transpose operator of the observation operator, so that your vector now comes back to the state space. And K is just a scalar, which will be usually positive if you want a feedback to the observations. So if we use this simple choice, what we get is the following equation. So the solution at the next time step will be the solution of this equation. And the solution of this equation is the same as the minimum of the following cost function. If you look at this cost function, there are three terms. The first one in black just ensures that, well, it's a square norm of x minus xn. So basically it ensures that the new solution at the time step n+1 is close to the previous solution at time n. The red term is simply also a square norm. It's a quadratic distance to the observations. It's very similar to what you can find in 4D data assimilation scheme, where you also want to minimize the quadratic distance between the observations y and the corresponding model solution hx, using again the R-1 covariance matrix. And the blue term is basically the energy of the system. So a very simple way to understand that is typically if you consider the heat equation, where the time derivative of the solution is just given by the Laplacian, which is the second space derivative of the solution. Then you get minus Laplacian of x dot x, which is the same as plus the square of the gradient of x. So it's really the energy of the system. So that if your model equation comes from a physical principle of, let's say, conservation of energy, this is the same principle that you'd get here. So that at each time step, when you solve a model equation with nudging, you basically minimize, you are doing a compromise between minimizing the energy of the system and minimizing the quadratic distance to the observations. So it's not so different from 4D algorithm. But it's also very, very similar to Kalman filters. Because in both algorithms, when there are no observations, basically in the nudging, you can just solve the model equation without any feedback, which is just the forecast step of the Kalman filter. And when there are observations in nudging and in Kalman filters, you basically update, you correct the model solution with the innovation vector. So that if, in some sense, you choose optimally the nudging gain matrices at any time, what you will get is exactly the Kalman filter. Of course, we usually don't optimize the gain matrices at all time steps, for a simple reason is that at least in France, mathematicians are quite lazy, so that we just try to do simple things. So we will consider much simpler matrices so that it's a kind of suboptimal Kalman filter. Okay, so let's try to understand why it works on a very simple linear situation. So again, this comes from Leuenberger in the 60s. So I'm assuming that there is no model error, and I will also assume that there is no observation errors. So that X true is supposed to be the true solution, the true state of the system. I'm assuming that the true state is a solution of the model equation, so that the time derivative is equal to f X true. And I'm also assuming that there is no observation error, so that what we observe, y, is exactly the true state through the observation operator. So nudging is simply solve dx over dt equal fx plus the feedback to the observations. And if we simply take the difference between the two equations, one for the true state, one for the observer state, what we get is that the time derivative of the error, the difference between the nudging state and the true state, is simply propagated, simply given by this matrix f minus kh times the error. So f is the model, and minus kh is basically the gain part. So if this matrix is what we call a Hurwitz matrix, which means that all the eigenvalues have a real part strictly negative, then it's quite easy to understand that x minus x true will converge asymptotically to 0 when time goes to infinity. You can see it in dimension 1. If the time derivative of something is given by some number times itself, the solution will just be the exponential negative, well, it will be the exponential, a time exponential with this value inside the exponential. So basically, if this is negative, let's say -1, the solution will be exponential minus t. If this is -2, it will be exponential minus 2t. So that when time goes to infinity, this goes to 0 exponentially quickly. So it's the idea, and that's why it's called asymptotic observer. No, I'm slide 9. Is there an issue in my sharing? So do you see slide 9? Yeah. Okay. So
I don't know if you.
Sorry.
Yeah, I can see slide 9.
Okay.
Right.
Okay, so it's why it's called asymptotic observer, because it's asymptotic in time. Basically, it decreases like a negative exponential in time. So there is a nice mathematical result, which is the pole assignment method or pole placement method, which basically says that if a system which is composed of a model F and an observation operator H is what we say observable, which means that basically we observe enough information to be able to reconstruct the system, then for sure there exists a matrix K such that all the eigenvalues of F minus KH are negative. So that in this case, we are sure that we can make the nudging solution converge asymptotically in time towards the true state. Okay, so let's look at a very simple example, which is not geophysical, it's a toy system in dimension 2. Let's assume that there are two variables. So x is a vector with two components, x1 and x2, and let's assume that the dynamical system is simply the time derivative of x1. So x1 dot is x1 plus x2, and the time derivative of x2, x2 dot is also x1 plus x2. If we look at the eigenvalues of this system, we basically see that the two eigenvalues are 0 and 2, which means that in some direction the system does not evolve, and in some direction the solution will just grow exponentially in time. And we assume that, for instance, only the first component of x is observed, so that the observation operator H can be seen as this simple matrix, which is just a projection onto the first component. So that if we look for a gain matrix, it should have this shape, K1, K2, And the goal is to find K1, K2 such that F minus KH has all its eigenvalues negative, strictly negative. So if we compute F minus KH, this is what we get. And because we observe only the first component of X, we basically can play only on the first column of F, because we will basically change only the first component of X. But the model itself will couple the two components so that it will indirectly also change X2, the second component. So if we look at now the eigenvalues corresponding to this matrix, there are many choices, and typically if we choose K1 equal to 4 and K2 equal to 5, both eigenvalues will just be -1 and -1. So there are many other choices, but this one, the choice of K, which is 4 and 5, will lead to two strictly negative eigenvalues, -1 and -1, so that the system is stable, and the error will asymptotically decrease in time with an exponential -t, because the eigenvalues are -1. So if we just look at the error, if I'm starting from a point 10, which is not the true state I'm assuming it's 1 minus 2. So as you can see, the first component is already correct. It's the one we observe, but the second one that we don't observe is not correct. But so the top line is in the case of no nudging, and so that we have the good, so what is plotted is just the first component of X, so that at the beginning it's the good one, it's 1, and because the second component is not correct, if we don't do anything, the first component becomes wrong, compared to the blue curve below, which is the true solution. If we start to put some nudging, typically in the case 1, we choose K equal to 2 and 2. This will lead to eigenvalues 0 and 0, so that the error will just actually remain constant. There will be an exponential of 0t, so just a constant. So of course, it's globally for the two components. So here the first component has an increasing error, and then it becomes more or less constant. And then if you increase K, you basically decrease the eigenvalues, -1, -2, so that the solution will converge to the true solution. So again, it's asymptotic in time, so it would need an infinite time to get the exact solution. But like this, you see that you can choose, in some sense, the decay rate of the error. You can go as fast as you want. Of course, in real life, we have nonlinear models. So it's still possible to get theoretical results if we assume typically that some part of the model is linear, so F represents the linear part of the model, and G will be the nonlinear part of the model. So it's a nonlinear function. And we basically need to assume that G is differentiable and Lipschitz, which means that it's a kind of strong continuity. When two states are close, x1 and x2, then the model output g of x1 and g of x2 should also be close. Yes, when the model is observable, we can always find some k such that the eigenvalues are negative, yes. So here also we assume that the system is observable, so that we know that the linear part of the model can be controlled and f minus kh can be stable. The point is that there is also the g function in the model equation, and this one might be unstable. So if we do exactly like in the linear case, the nudging equation will be dx over dt equal fx, the linear part, plus g of x, the nonlinear part, plus the feedback to the observations. And still assuming that there are no observation errors, which means that the observation y are just h x true. In this case, again, by taking the difference between the nudging equation and the true solution equation, the error between the nudging state and the true state will be propagated in time by this blue stable part and the red nonlinear part. And the idea will be to try to control, to get more than stable with the blue, to get more than strictly negative, to be able to control the red part. And typically, because of the Lipschitz continuity of the nonlinear function g, we can prove that very easily that it's kind of energy estimate. The time derivative of the square norm of the error will be at most the largest eigenvalue of f minus kh plus L, the Lipschitz constant of the nonlinear function g, times the squared error. So that now the goal is not to get all the eigenvalues of f minus kh negative, but smaller than minus L. So that even with the nonlinear term that might make the solution increase, you can get something that will decrease asymptotically in time. And again, that's possible to shift the eigenvalues to more than 0, to minus L. So one simple nonlinear example is the Lorentz system, which is a very funny differential system in 3D. So it's very well known, and it's, at least for I would say mathematicians, is the first toy model that we can consider before looking at more geophysical models. So it's a nonlinear model. There are nonlinear terms like here, xz and xy here. Sorry. And there are parameters, sigma, rho, and beta, and these are the typical choices to get chaotic behavior with the famous butterfly shape of the solution. So this model can be decomposed into a linear part like this, and a nonlinear part with the two nonlinear terms xz and xy. And assuming that the trajectories we consider are bounded, so that they don't go to infinity, which is usually the case with these parameters, because we have two attractors, one here and one there, then we can prove quite easily that the g function is Lipschitz continuous. So that it should work. This is a very simple way to do nudging. And of course, we have to choose the K matrix in such a way that the system is stable. So I won't get into details, but if you want to prove that a linear system is observable, you basically need to prove that the observator operator H, the observator operator times the model operator HF and HF square. So it's because we're on dimension 3, so we stop at 3 minus 1. This matrix should be invertible. In this case, we say that the system is observable, and then we can place the eigenvalues. So if we choose, for instance, H equal to 101, which means that we observe X and Z, but not Y, then in this case, the matrix is invertible, the system is observable, and then we know that we can do it. If we observe just X, or if we observe just Y, in this case, we cannot prove that the system is observable like this, which means that maybe it's not observable, but we can prove that it's still possible to actually control the system and find gain matrix K such that you have stable solution. For instance, I choose to observe only X. So only X variable is observed, not Y, not Z. If I choose this particular K matrix, then F minus KH will be this matrix, which is a triangular matrix, so that the eigenvalues are simply on the diagonal, minus sigma, minus 1, minus beta, so that they are all three strictly negative, so that it will work. There are many, many choices, of course. So this is another way to design the observer. So basically, you should look at this one. This system, in black, you can see the original Lorentz model. And in red and blue, the additional terms that come from nudging. So again, only X is observed. So I'm assuming that I know X true, because again, I'm assuming that there are no observation errors. And by using these terms in X true minus X for the feedback on Y and Z equations, and actually nothing in the X equation, then this will work, because we can prove again that the linear part of the error will be this matrix with eigenvalues minus sigma, minus 1, minus beta. And the nonlinear part will be given by this matrix here. And if we look at the eigenvalues, we basically can see that one eigenvalue will be minus sigma, which is strictly negative, and the two other ones, because beta is strictly positive, the coefficient in front of lambda 1 plus beta is strictly positive. Also, the constant coefficient is strictly positive, so that the eigenvalues, the roots of this polynomial will be strictly negative. So the error will decrease. And if we try, this is what we get. In blue, you have the true state with the true initial condition, which is this one. In green, you have the wrong state with the wrong initial condition, which is basically the opposite. If we don't use any nudging, of course, you cannot get back to the true solution. But if you use the observer we have seen just before, in red, this is what you get. So asymptotically, you'll get to the true state. So this is the X variable, the one which is observed. And these are the Y and Z variables that are not observed, but they are corrected thanks to the observations on X. And they also converge, the nudging solutions also converge toward the true solutions. So this is the evolution of the norm of the error between the true state and the nudging states versus time in log scale, because it's given by some negative exponential. And basically here, the largest eigenvalue is close to -1, so that you have this kind of slope. Okay, so here, the frequency observation, I'm assuming that I'm observing every time step. I will give, in further examples, cases where we observe sometimes and sometimes we don't observe. The funny thing is that theoretically, you can prove that it works exactly the same. Sometimes even the decay rate of the error doesn't change if you observe only partially in time. Of course, usually numerically, you see that it becomes slower if you have less observations. So the point is that theoretically, it's quite hard to assume that you observe at only one time step, so that you should, mathematically speaking, you will need direct functions, and it will be harder to prove something. But we can reduce, we will see, we can reduce the observation time and see that it still works more or less the same. Okay, so let's see even more complex observers, because at the very beginning for the nudging, the idea was basically if you observe some variable, let's say the velocity, you will basically correct the velocity in the velocity equation with the velocity information, and that's it. The idea is that there is no hope to observe all the variables of your system usually, but of course we want to correct all the equations so that all the variables will get corrected and converge to the true solution more quickly. So the idea is that formally we want to be sure that all the non-observed variables are controlled by the observed variables. So here it's a more geophysical system, which is a shallow water model. So in 2D, but it works also in 3D. So the two variables are h, the height of the water, and v, the velocity of the water. So it's a very simple model. I'm just assuming that the height is the water is just propagated by the velocity, and same for the velocity, and there is also gravity, so that water wants to become flat. So I'm assuming it's a very simple domain. It's a square domain with rigid boundaries, mostly lateral boundary conditions, etc. So assume, if you think that it's a huge swimming pool that may look like the Atlantic Ocean, assume that you can observe only the sea surface height, h. There are very few observations usually of the velocity, so let's try to correct both the height and the velocity of the water from only observations of the height. So very generally speaking, the observer would look like this. We would solve the same equations as the model equations plus some feedbacks. There will be one function in each equation. And the feedback term is a function that will, of course, depend on the observer variables that we compute at each time step, and also the observed variable. So h ops is the only thing we know from the true system, the observation. So if we just make some simple assumptions, one, for instance, is that if h is equal to h ops, which means that we have the true height, we would expect these additional terms to be equal to 0, typically. We will also assume that these terms will preserve the symmetry of the model. So typically for this model of propagation of water, it's invariant to translations and rotations. So the observer should also be invariant to translation and rotations. We would add some smoothing, typically by convolution kernel, so that if the data are noisy, then you will filter on the noise. And we want, of course, local stability in the sense that at least the linearized system must be asymptotically convergent. The error must decrease asymptotically to 0. And using all these assumptions, the most simple observer that we can find is the following. For the height equation, basically, it's just a convolution kernel that will smooth the observations times h minus h ops. So basically, we just correct with a simple feedback term. And for the velocity, the most simple one will be to use the gradient of the height as a feedback for the velocity. And again, we use very simple kernels that are invariant by rotation. So just a kind of Gaussian kernels to filter noise. So if we use that, if we linearize the system to study the linear error evolution, what we can get is that, so with a tilde, it's basically the error between the true state and the nudging state. The error is a solution of a kind of damped wave equation. So second order time derivative and the second order space derivative with some damping. And it's very easy to prove that the solution of this wave equation will converge to zero asymptotically in time. So this is basically what we can prove, that both the height and time derivative of the height will tend to zero strongly in time. And we can also prove that for the velocity, so that all the solution, all the state will be corrected and will converge to a true state when time goes to infinity, including the velocity. So this is what we can see. So typically here we use noisy observations, and we assume that the observations of the height are available everywhere and at any time for the beginning. And this is the evolution of the error versus time. And the good point is that the decrease of the error is the same for all three variables, the height and the two components of the velocity. So that again, you can, from just observation on the height, also correct the velocity. And if we plot at the evolution of some particular points, if we look at the height at a specific location in the domain to see versus time what we get, because we start from something which is wrong at the beginning of the blue compared to the true state in black, this is what we get. So it's quite noisy, but of course we have probably way too much observations in time. But you can see how it works, and thanks to the smoothing operators, it's also reasonably filtering noise. So we have done similar things for more complex equations. Typically here it's a compressible Navier-Stokes equation. So the variables are rho, the density, and u, the velocity. Using the, so just a funny thing maybe before, the very funny thing is that when we showed this to colleagues in geophysics, they told us, well, it's well known that there is a kind of geostrophic equilibrium in which the gradient of the height of the water should be more or less equal to not the velocity, but the velocity rotated due to Coriolis force. And the funny thing is that we don't need to rotate this gradient to actually control the velocity. We tried to add a kind of Coriolis force to rotate by 90 degrees this gradient, and it gives exactly the same result. So that sometimes you can use physical information, sometimes mathematical information also work. So here it was the same. We basically wanted to design observers, the blue terms, in such a way that we still preserve the standard properties of the system. And also, we don't want to use too much differential operators because the observation will be noisy. So we don't want to take too much derivatives of noisy information. And the thing is that in any dimension, For any mode K, because all these are based on Fourier decompositions, so up to any frequency, we can find convolution operators, including differential operators, such that the decay rate of the errors on both the density and the velocity will converge to 0 at so the decay rate will be at least what you want. So you can arbitrarily choose the decay rate for any frequency up to any frequency capital K. And the point is that for the very, very large high frequencies, usually it's just noise. And if there is some diffusion in your equations, theoretically or numerically, these modes will disappear anyway very quickly with time. So that you can choose the decay rate arbitrarily large and get your observer work, actually. So that either using density observations or velocity observations, it's completely symmetric. You can get both density and velocity. So for the parameters, alpha and beta, so alpha here is the kind of radius of the smoothing of the convolution kernel. So typically it should be linked with the level of noise that you have. If you take a very small alpha, so if you take a very large alpha, you'll get back to standard nudging where you just use the same location for the observation and the correction. If you take a small alpha, you'll use a mean of your observations around on circle around your location to correct at your location. And beta is just a kind of weight. That's typically the weight you will need to choose if you want to choose your decay rate. And usually the larger beta will be, the faster the convergence will be. So no, there is no automatic strategy. At least for beta, you can get a theoretical limit value so that you should choose beta larger than something to be sure that it works, so that you can simply choose beta just equal to something slightly larger than the theoretical limit value. And alpha again is linked to the noise on your observations, so that you have to tune it depending on the amount of noise on your observations. So typically we can get this kind of decrease of the error versus time depending on the values we use for these constants, phi u and phi rho, that correspond to the two equations on the velocity and density. So the funny thing is that one of the two variables will basically mainly act as the decay rate. So you will tune the decay rate with it. And the other one will mainly, because it will mainly tune the real part of the eigenvalues. And the other one will basically tune the imaginary part of the eigenvalues, so that if you choose it in a good way, you can get a decrease which is a straight line with no oscillations. Otherwise, there are complex parts in the eigenvalues, so that your function is, the error is oscillating like cosine or sine functions, which might not be good. So one will be here to tune the decay rate, and the other one will be to, in some sense, remove the oscillations. So again, here there are formulas. You can just get your values for a given decay rate. You can find values, phi u and phi rho should be this. And of course, it works also for a nonlinear observer numerically, because for any linearized situation, it works. And we get a very simple same things. So on the right, typically, here we assume that we don't observe everywhere in space. The space domain is 0, 1. So we can observe on the full space 0, 1, and you'll get this decrease. And you can reduce the observation zone and assume, for instance, the first one is that we observe only 10% of the space domain. And this is what you get. So of course, theoretically and numerically, you lose about the decay rate for the same parameters, but even for a partial observation zone like this, you can tune the parameters phi u and phi rho to get this decay rate again. So by changing the nudging coefficients, you can get back to this decay rate if you want. So we are currently working on the same with compressible Navier-Stokes with an image, which is a kind of passive tracer. So assuming that this would be the information we have, kind of images of a passive tracer. It can be a chlorophyll or something like that, or clouds for weather forecast. And we are trying to recover from observations of the image, recover the density and velocity. So theoretically it works. We have all the theorems, we have all the bounds, but I don't have numerical results yet to show you. So it's a ongoing work currently. Maybe I will skip this. It's also another application with a shallow water wave. Okay, so the second point is that usually for operational reasons, we don't have infinite time. Just like for my talk, I'm supposed to stop at some time, so that the time scale might not be long enough to get convergence. So the idea will be to actually iterate, to use forward and backward nudging in forward and backward time to run again nudging on the same window, time window, so that we'll have enough time or enough iterations back and forth to let the observer converge asymptotically. So the idea is, if you have a numerical model, you can try to solve it backwards in time by typically you just reverse time, you just tune and set time step to be negative in the code and see what it gives. And we can, of course, apply nudging to this backward model. And because it's not, how to say, because if you can do it once, solve your model forward in time with nudging and then backwards in time with nudging, you are back to the initial time so that you can iterate and start again. And this is the basic idea of the back and forth nudging algorithm, where you start from a first guess and then you solve forwards in time the model equation with nudging, and once you reach the final time you solve the model equation backwards in time from capital T to 0, again with nudging, and you iterate. And the idea is that if you look at the forward and backward equations, they are the same. But of course, because the time goes forward for the first one and backwards for the second one, the feedback term has an opposite sign. And the thing is that if you basically look at the sum or difference of these two equations, so the sum would make the nudging term disappear, so that the mean of forward and backward solutions are solutions of the model, and the difference of the two equations implies that the red terms are equal to 0, so that basically your solution will fit with the data. So the gain matrices are fixed in a very similar way as nudging. For the forward, there is basically nothing to do except there will be a small k here to tune if you want more or less nudging, depending on probably depending on the number of observations you have. And backwards, the idea is that you probably need to stabilize the backward resolution of the model, because usually we consider irreversible systems because of diffusion, typically. So that if you solve it without nudging, it will probably be unstable. Numerically, it will diverge. So that you should increase the nudging matrix by choosing at least the smallest value that makes the backward numerical integration stable. So we started to prove a lot of things on transport equations. So here it's in 1D, but it works in any dimension. The time derivative is given by some velocity times the space derivative. There is also viscosity with a second derivative, and this is the feedback to the observation. And what we can prove is that if the system is fully observed in space, but not in time, the error will decrease asymptotically in time in the same way. If the domain is not fully observed, because of viscosity, it will become ill-posed, so it will not work. But the good thing is that after k iterations of back and forth nudging, the error has been decreased by this exponential here, so that the error decreased exponentially thanks to three things. The first one is the feedback, the size of the feedback. So of course you could increase the feedback towards infinity, which is probably not physical and also not interesting if your observations are noisy. You can also increase time to infinity, which is just the asymptotic observer. Or if time is fixed, you can increase k, the number of iterations, to infinity. And in some sense, instead of doing nudging over an infinite time window, you do it infinitely forward and backward over a small time window. And by symmetry, when you are going backward, it's just like going forward with the backward model. So that with an infinite number of iterations is the same as doing it infinite time. So this is the kind of results we can get. Typically, if you have partial observations in space, theoretically it's ill-posed, but numerically it will work if you wait enough time. Simply, it's just a kind of observability condition. It's a transport equation, so things are moving. If you just observe at some location, you need time so that everything will move in front of the camera so that you can see it. So let's look at a shallow water model. Again, our huge swimming pool of 2,000 kilometers, which looks like the North Atlantic Ocean, you see, with the Gulf Stream here. So this is the sea surface height, which is larger than the mean in red, lower than the mean in blue. So here it's a kind of reasonable system where we assimilate observation over 15 days. We assume that we have observation only of the height with noise, sparse in space, sparse in time. We use a wrong background state, etc. So we'll try to do things reasonably realistic for satellite observations of an ocean. And this is what we get with the back and forth nudging iterations. So as you can see, maybe, so there are 5 iterations and the ocean is turning right and then left iteratively. So here it's going forward. So it's a standard case where hot water comes from the left to, so US to the right of the ocean, Europe. And backwards, you simply push back water to US. After 5 iterations, we will compare with the true state here, the background state if we don't do any data assimilation, and the Ford-Ivar with also only 5 iterations, which means that it did not converge yet. And this is what we get. So the background is quite noisy. The Ford-Ivar did not converge again. Oops, sorry. So maybe, okay, we can wait again. And the thing is to compare what we get with the back and forth nudging with the true state, because of course it's twin experiments, so we know what the true solution is. And even with quite poor initial condition and with noisy observation, you basically see the grid of observations. It's all these locations that you can see. You get a quite nice solution. So the same observations, when they are available at some time, they are used at this time and only this time at both forward and backward resolution. So the same observations are assimilated over and over, forward and backward. So as you can see, the location and the shape of the vortex is quite nice, and that's quite reasonable. We have done it also on maybe more realistic model. So here it's a quasi-geostrophic ocean model with so it's more than just a swimming pool. It's a quite realistic 3D topography. And for the SWOT satellite mission, which is maybe will be launched this year. So when we started, it was supposed to be launched in 2018, I think. So maybe people hope it will be launched in 22. So it will provide quite large bands of observations of the SSH with 120 kilometers. And this is what we get in 5 days, in 10 days, and in 21 days. So basically in 21 days, you get the full coverage. And we can prove on quasi-geostrophic ocean model equations, theoretically, that there is a Lyapunov function, which is a kind of energy function that asymptotically decreases to 0 when time goes to infinity, which means that theoretically it will ensure the convergence of the nudging in infinite time or the back and forth nudging over a finite time window. And here, typically, we can prove that the convergence rate is not impacted by data frequency availability. So typically, on the left and the right, you have the decrease of this Lyapunov function versus time for the forward iterations in blue and backwards in red. So for 10 iterations. On the left, it's when you have one observation available every 10 time steps, on the right, one every 150 time steps. And this is what you get. Actually, there is no difference, except that on the left, it looks more continuous because you use observations almost all the time. On the right, it looks more like a Kalman trajectory with kind of stairs when you do correction, when you have sometimes observations. So typically here it's a case where time frequency will not change anything. And this is what we get with SWOT-like data. So typically we assume that we have sparse data according to the tracks of the satellite with noise. So they are more or less realistic, even if the satellite is not launched yet. And this is what we get for a decrease on the left, and on the right you have the exact situation, and at the bottom the assimilated SSH. So it works quite well, and it's quite simple to implement this. You can do it, the back and forth observer can be done with something more complex than just nudging. So typically here it's a kind of a Kalman filter. So it's a reduced Kalman filter, but so again, so here it was simulated with Topex Poseidon tracks for the SSH. It's back to a shallow water model. And this is the example of data that we can assimilate every day. So quite sparse. And on the right, you have the true SSH. On the left, the identified SSH at the beginning. So here there is nothing done. It's just the background, which is slightly different. Here it's after 2 iterations back and forth. So basically we have done 4. We've used the observation 4 times, twice forward and twice backwards. And after 4 iterations, this is what we get. So again, the starting point, 2 iterations and 4 iterations. So it's quite efficient, and you quickly get a nice solution. So this is the decrease of the error on the SSH along the iterations, as you can see. Okay, so one thing, what we have seen is that when we need to solve backwards in time, we might have an issue with diffusion, because it's typically an unstable thing when you go backwards in time. So if you just look at the heat equation, which is the equation where you just have diffusion, there's nothing else. When you want to solve this backwards in time, it's equivalent to solve this forwards in time if you make a change of variable by reversing time. So that basically your equation, instead of being just diffusion, is anti-diffusion with a negative sign. And theoretically, it's an issue because the second derivative operator has unbounded eigenvalues, so that you'll get something unstable at any time, any speed, it will be unstable. Except, of course, for a discrete operator where all the eigenvalues will be bounded because it's in finite dimensions. So the thing is that usually for geophysical applications, diffusion is not a dominant term, and even sometimes it's not a physical term. Typically for atmosphere, usually the equations are Euler's equation without viscosity. So of course, people add a small viscosity either to stabilize the numerical integration of the model, or to model sub-grid physical processes, but it's typically not really diffusion. And the funny thing is that theoretically, if we are back to a transport equation, for a viscous linear transport equation, we can prove that it's ill-posed. There does not even exist a solution to a backward model. And for a viscous Burgers equation, which is nonlinear transport, it's also ill-posed because there is no stability with respect to the initial condition. While without viscosity, we can prove the convergence. So it was the idea of a small extension of these back and forth observers was to say that actually in the geophysical context, the diffusion is there mainly to stabilize the numerical integration of the equations and also to model subscale phenomena. And for instance, if you look at a quasi-geostrophic ocean model, sometimes you will see this kind of operators. So 4 for 6 derivative for dissipation at the bottom or for vertical mixing. And the idea is that we, as mathematicians, will consider these are artificial diffusion terms. And if they are artificial, we can consider that when we solve backwards in time, we can also reverse the sign of these diffusion terms, so that also in the backward resolution, we have stabilization of the numerical integration and the same subscale phenomena modeling. So that only the other, let's say, physical terms in the model will be solved backwards. So that here is the standard forward equation with the model, with the artificial diffusion, and with the nudging feedback. And backwards, we will solve this one, or if you change the time to get back to a forward time, we will actually solve this equation, so that if you compare with the first one, only f has a different sign. So you basically change the sign of the main terms in the model. So typically, if it's a transport, you reverse the transport. So that's what we have seen with the movie. Water moves back to the west part of the ocean. The funny thing is that, so K and K prime could be different, but, well, if you first set K prime in such way that you have no issue with the backward equation, you can choose the same for K in some sense. So assuming that typically here we can choose K and K prime equal, and if we look at a simple transport equation like this, if we apply this back and forth nudging algorithm, we can prove that at the limits, when the number of iterations go to infinity, both forward and backward trajectories are the same. And they are basically solution of the blue plus red terms equal to 0. And also the black equal to 0. Same as before, if you do the half sum or half difference of the two equations, you will see that f is equal to 0, and also the blue plus red is equal to 0. So blue plus red is equal to 0 is this, the diffusion, the artificial diffusion plus the feedback to the observation is equal to 0, which can be rewritten like this. And this is a very well-known equation in signal processing. It's called standard diffusion restoration equation, where you basically say that given observations that are noisy, you recover a solution which is equal to that up to some smoothing operator. So it's basically the same as to process the noisy data with a kind of Gaussian filter that will smooth the data. And this is what we can get on a simple transport equation. So here it's a constant transport, so that things are just moving at constant speed, forward and backwards. So you see that it's going to the right, to the left. And in blue, this is what you get after a couple of iterations, starting from 0. And it already converged. And this is what you get at the end. And the funny thing is that if you consider the true solution in red, if you apply the smoothing operator, a kind of Gaussian operator, you'll get exactly the blue curve. And this is the decrease of the error versus time in standard scale or in log scale with the forward and backward iterations. We did that also in shallow water, and this is what we get compared with the original back and forth nudging. So it's not very different, except that it's less noisy. It's maybe not completely obvious here, but it's less noisy. And it's very similar to what we get with 4D VAR at convergence, which required here almost 50 iterations. And you see that we are very close to the true state. Okay, so we did that also on a full primitive ocean model with also quite realistic observations. Again, these are the top exposure tracks for the SSH every 10 days, and some vertical profiles of temperature to simulate the Argo float network. And these are the kind of decrease of the error we can get, again, versus the iterations of nudging forward and backwards. So here it was also, there was a need to, the point is that there is not much diffusion inside the model, not horizontally, but there is a kind of vertical diffusion that helped to mix the layers of the ocean. And this was hard to solve without reversing the mixing, so that when you solve backwards, you also mix and not unmix, in some sense, the layers. Okay, so just a few words on another extension of these. So we have done that with the nudging, but we can do it with more complex observers. Also with just forward observers. We are not obliged to do it with a back and forth on a small time window. We can do it with a standard forward observer on a large time window. So here the goal is to also estimate parameters. It's supposedly the main drawback of, let's say, Kalman filters and sequential data estimation schemes, that you basically correct the model solution, but maybe not the parameters. While variational algorithms like 4D VAR usually are able to evaluate, to estimate everything at no cost, no additional cost. So here the idea is to, it was an idea that has been seen quite recently, 10 years ago, for Kalman filters for medical imaging. People said, okay, we have some parameters. We assume that the model parameters are time independent. So they are space dependent, but not time. So typically here, I consider a simple transport equation. And the idea is that because the parameter is time independent, we can say that it's solution of a very tricky equation, which is the time derivative equal to 0. And then you just add this equation to the main model equation. And on that, you can apply a Kalman filter or a nudging observer forward or back and forth or whatever. And the idea will be then to, as we have done before, to correct multiple variables with only one. It's the same here. We will try to correct both U, the model state, and A, the parameter, with only observations on U. So that's, at least mathematically speaking, the parameter is just another variable of the model, another physical variable. And in a case of linear transport equation, we can actually prove that it's possible to design an observer that works asymptotically in time, so that both the state and the parameters are reconstructed. And typically, a very simple test case with a transport equation. So on the left, you have the solution, which is just transported by a non-constant velocity. The velocity is in blue on the right, it's the parameter. So the velocity is larger in the middle of the domain and smaller on both sides. And we have only observations partially in time and space on the state. so that we can correct the state, but also correct the parameter, as you can see. So sometimes nothing happens because we have no observations, so we do nothing. And when we have observations, then you correct the solution, so you can see that it will evolve in time. So the state, of course, is corrected much more quickly, but the parameter also is corrected. And after a couple of iterations, this is in red, the identified parameter that we got. And this is the decrease of the parameter error versus time along the back and forth iterations. Again, if we have a long time window, we can do it simply forward in time, and you will see the decrease over time. We have done that also on the quasi-geostrophic model with a SWOT data, where the parameter that we wanted to identify is the phase speed, which is linked with the barotropic deformation wave number. So on the left, we have the true parameter, the one we use to generate the observations, so that if we just want to recover the state, this is what we get. The error decreases exponentially in time versus the forward and backward iterations. And then the forecast is good because the parameter is good. What's the level of noise? That's a good question. I think there was no noise here. I think there was no noise in the observations. Just a proof of concept. So here, for SWOT data, it was standard noise according to what the satellite is supposed to provide. So this one is much more realistic. On the right, assuming that the parameter is wrong, but not corrected. So we use basically a wrong model with a wrong parameter. We start from the wrong solution, and we have observation of the good solution, but according to the satellite tracks with noise, of course. And as you can see, it's more difficult to make the error decrease. And once we almost converged for the forecast, because the model is wrong, the forecast becomes wrong quite quickly.
Didier, 5 minutes.
Yeah, sure. And on the left, this is the case where we jointly estimate the state and the parameter, so that each time we assimilate observation, we change, of course, the model solution, but we also change the parameter, so that at the end, we still have a quite nice identification of the initial condition, but we also keep a very nice forecast because the model has been corrected, because we have now an almost good parameter. And on the right, this is the evolution of the error on the parameter. Well, it's not exactly the error on the parameter, it's the Lyapunov function, which is more or less the square error according to the parameter versus time with the forward and backward iterations. So again, you can see that it decreased to 0 quite quickly, so that at the end, the model parameter is identified. Okay, so to conclude, so we looked at nudging because it was very simple to implement and very efficient in the first iterations. And of course, we understand that it's probably not as efficient as a 4-divar or a nice Kalman filter, but it's a good preconditioner probably to get quickly close to a nice solution. And also, if you don't have the time or all the engineers to implement a 4-divar or full Kalman filter, it might be a good solution. We have seen how to deal with diffusion issues, of course, in a geophysical context. And we have seen using observer techniques that it's also possible to estimate model parameters at almost no additional cost. The thing is that it's no additional computational cost because there's human cost, which is quite large. We actually need to, for each time you change the equation, you need to recompute everything to find a good gain, a good operator for the feedback to correct the parameter. And it's of course the same if you want to correct other model variables. So it's really dependent on the equation and the parameters. But once you have done that, it works exactly the same. And of course, we have extended this to more complex observers using physical considerations, using Fourier decompositions, energy estimates, eigenvalue computations, etc. But it's very similar all the way, except that you change everything in your equations. And so we have extended this to parameter estimation as well. Of course, assuming that the parameters are time independent. If they are time dependent, I'm not sure we can still call them parameters, but it's probably more a model variable. That's it. So there's a question about nudging on a neural network model. It's a good question. The point is that, so you would like to use nudging to correct your weights, maybe on your neural network. Theoretically, it's possible, but if your neural network is quite dense, and it might be almost impossible to derive theoretically all the equations to see what the gain should be. On a simple neural network, yes, probably it's not a big deal. But on a more realistic one, I'm not sure it's very interesting. But the thing is that if you consider a neural network model, it probably means that you forget about the physical model, except if it's a physical inspired neural network. But if it's just a neural network that supposedly reproduces the mathematical equation, I would say that it's easier to work on the mathematical equation than on the neural network itself.
Didier,
yeah,
I have two questions. One is if you have some algorithm to what we need to pay attention when you apply this backward time equation. In particular, when we are dealing with the diffusion operator. And secondly, the same, because when you mentioned that we have at least two gains matrix, and so also how can I, estimate this in an automatic way?
So backwards, usually the only issue is with non-reversible terms, which are mainly diffusion or friction terms. So again, for geophysical applications, usually you should just change the sign of these terms, because if there is friction when water goes on one way, when water goes the other way, you would expect the same friction. So you should just reverse transport, but not friction, keep the same friction in some sense. For the second question, basically, so we usually don't use full matrices for the gain matrices. It will have the same shape, which is a very simple nudging, which is take your observed variable minus the theoretical variable, and this will be applied in each equation with possibly some differential operator. Typically, if it's a velocity if you want to correct the velocity with height, you'll basically take the gradient. And usually also convolution with a Gaussian kernel to smooth things. So not much to compute. And usually we take the same for the forward and backward. Usually we consider exactly the same value. And these values are given by the theoretical computation about the, if you want to prove that all the eigenvalues are negative. So also there was a question, can we use BFN method to estimate the parameters can be fed later to the ensemble Kalman filter? No, I wouldn't use that like this. I would use BFN as a kind of preconditioner to get a nice estimation of the model state or maybe model parameters, but then if you have an ensemble Kalman filter, just use it. Maybe starting from what you get from the BFN. It's a kind of very efficient preconditioner. So the thing is that if you want to estimate a model parameter, it has to be a parameter of something. If it's a parameter of your model equation, you can do it. If it's a parameter of a data assimilation method, it's not the same, because then you need to consider the data assimilation equations, not the model equations. And I'm not sure it's a good way to use a data assimilation method to improve another method that then you will apply. It's probably too complex. I'm not sure it would be a good way to do.
Okay, I would like to say thank you a lot for you, Professor Didier Ho. Very, very interesting, very nice talk. And I think that all of us, we have maybe more questions. And so my suggestion that if other people want to address a question for Professor Didier, please go ahead with that and email him if
yeah.